Okay, so to end our Algebra at IMPA meeting, it's my pleasure to introduce our fourth postdoc that will speak today, Juan Guzman. Juan did his PhD in National University of Córdoba in Argentina in 2022. And now he's here with IMPA. You've been in IMPA for a while,
For 1
right?
year. This is my second year.
Okay, so he's been here already for a year. And today he's going to tell us about Chiral homology of P1 and factorization. Thanks, Juan.
Thanks a lot. Well, thank you all for coming, and thanks to the organizer for inviting me. Yeah, as I said, I've been at IMPA for 1 year already. I've been working with Jethro Van Ecker and Raimundo Elbani, Tadeo Cardoso. We have a group here. We're working on chiral homology, and we've been getting some results throughout this year. So I'm going to try and explain those results to you, right? So I want to introduce what is chiral homology to you. I'm not going to assume any prior background about it, so feel free to ask any questions you want. It is quite similar to Lie algebra homology, right? So we're going to try to construct a chiral complex which is going to like take these inputs, right? We're going for Lie algebra homology, you have a Lie algebra, which is your algebraic object. Then you have a couple modules, and then you have your complex computing the homology using those ingredients. For chiral homology, we have that algebraic part, but we also have some geometric data. So for chiral homology, we're going to need a VOA, which is going to be our algebraic object, some modules for that algebraic object, and we're also going to fix a smooth curve. And here, when I say curve, I mean a complex algebraic curve, right? So you can have any genus that you want, but it's a complex algebraic curve. And you're going to fix some points, and you're going to think of the modules for your VOA, your algebraic thing, as things that are living or that are inserted at those points. So with all of that all of those things, which are kind of algebraic and geometric at the same time, you build up some complex, which we're going to call the chiral complex, and the homology of that complex will be the chiral homology. So it is a nice interplay between algebra and geometry, and we're going to get some algebraic results out of these geometric constructions. In two particular cases, we're going to study the chiral homology of the sphere of P1, and then we're going to basically, we're interested in what happens when you take 0 and infinity in P1 and you glue them together. You get a nodal curve in that case. So we're going to study how to define chiral homology for those nodal curves and see what we come up with. There's a nice phenomenon that's called factorization, which has been for a long time very well known. And we were able to generalize it a bit. So it's been really, really good. And for P1, for the sphere, we were able to first prove a result for the first chiral homology group, and then basically these last few weeks we managed to generalize it to any chiral homology group. So these are the main things that are going to appear in this talk. Let's start with the algebraic part, right? So the basic algebraic thing is going to be a vertex algebra, which in my head I always think about it as a vector space with a bunch of multiplications, right? Multiplications that are here, like nth products for each n in the integers, very similar to the ones that Lucia mentioned. Yeah, conformal superalgebras are basically very similar, but in that case, you only have nth products for non-negative integers. Now we have it for all integers. And we put them all together into a series, a formal power series, and we're going to ask for that series to be a Laurent series. And we are going to have a vacuum vector, which is going to be the unit for this algebraic thing. And there are several ways to define axioms in this setting. And there are several ways to do it because vertex algebras are in a way like Lie algebras and also like associative commutative algebras. They have some properties of both worlds, so you can define them with axioms in one world or the other. But since I'm going to try and move to the geometric side of the picture, we're going to define them with these residues, which are going to appear naturally when we construct the chiral complex. This is called the Porcher's identity. And OK, so with those axioms, you get a vertex algebra. So far, no geometry. And you can easily construct the definition of a V module, right? You get a map very similar, and you ask for the action of the identity to be trivial and for a very similar Borcher's identity. So, okay, these are the algebraic things, right? Now, in order to go to the geometry, these are not going to be enough, right? That's the reason why we take VOAs and not vertex algebras, because we need an action of the Virasoro algebra, right? So we're going to have this vertex algebra that I mentioned, and we're going to assume that there is a vector called a conformal vector, whose associated field here will give us a representation of some central charge of the Virasoro algebra, right? We're going to ask for some compatibilities, right? We're going to ask that L0 is semi-simple, and then its eigenvalue decomposition will give you like a grading, like a set. For vertex operator algebra, right? So in this way that I'm presenting it, it should be called a conformal vertex algebra because it's a vertex algebra with some conformal properties, but it's been known as VOA for a long time, since the beginning. And yeah. So basically, we're going to have another a conformal vector, which is going to give us the relation to the geometry. And why am I going to talk about geometry now? Because for the Virasoro algebra, we can lift it, we can integrate it to an action of this group, the group of automorphisms of the formal power series. And that can be interpreted as the group of formal changes of coordinate over the formal disk. So we have the first really geometric stuff appearing, which is a formal disk. And with these extra axioms, we get an axiom of its groups of formal changes of coordinate. Okay, so that's for the algebra itself. For the modules, we ask for some compatibility, right? We want the modules for the VOAs to be admissible, which means that they have to come with a grading. The grading has to behave well with respect to the end products. So no problem. I'm going to talk V mod is going to be the category of admissible V modules, and it's an abelian category, so fine, we can do homological algebra without any problem. With an extra technical condition, we get also an action of this automorphism group on the modules themselves. So, okay, no problem so far. And now we're going to try and build something with a curve, right? We have now the algebraic object, their modules, and now what happens when we add a curve? Okay, so the action here will allow us to define a bundle over the formal disk, right? So it is going to be something, since the formal disk only has one closed point, it's going to be only one fiber, basically, and that fiber is going to be the vector space itself. But thinking about it as a bundle, and more importantly, the sections of that bundle, we can look at the global sections, and the global sections are going to be this series, this module of the formal power series. And when we look at sections away from the closed point, we're going to get the Laurent series. So those are the elements that appeared in the product, so it's natural for them to appear here. And the thing that we can do now is we can, for any smooth curve, we can glue together all of these bundles that we get on each one of the smooth points, and you get a vertex algebra bundle over the whole curve, right? There's also like a more formal way to do it if you want this as an associated bundle. But I think of this picture very, like in my head, this is a picture. And the final result that we got is a bundle over this curve, more or less because it's infinite dimensional fibers, right? Forgot to mention that as well as conformal superalgebras, vertex algebras are always in more 99% of the time are always infinite dimensional objects, and all of the things that are appearing here are infinite dimensional in general. Okay, so we have this bundle. We're going to look at the sections, right? And the sheaf of sections is going to give us an O module over the curve, and it comes with a flat connection, so it's in fact not only an O module, but a left D module. And there's a canonical way to transform left D modules to right D modules, which is tensoring by the canonical sheaf. So that is going to be the object now. So from the vertex algebra, we constructed a sheaf over the disk, then a sheaf over an O module over the curve, any smooth curve that you wanted, and then that gives you a right D module. Okay, so why did we do this? Why did we insert all of this geometry? Well, because for right D modules, there's a whole other theory by Beilinson and Drinfeld of chiral algebras. And it ends up that this construction actually gives you a chiral algebra, so you can do a lot of things with that information. So for the curve, again, I'm fixing a smooth curve here. We're going to take their diagonal map, and the complement of the inclusion of the complement of the diagonal. Those are going to be these maps, delta and J. And now we're going to define a chiral algebra very abstractly. Yeah. Yeah.
The way that you phrase it seems that it depends only on the points, right?
Yeah, basically, this is the informal picture. The actual definition is you grab, you construct a bundle, this thing. You construct this living over the curve, right? So basically, it's a principal G bundle for this group, G, the automorphisms. So you construct a principal G bundle, and each one of the fibers are going to be basically the automorphisms of the local coordinates over the points. And then you do the associated bundle construction with that thing, right? Because you can do this.
Oh, it's not that you are choosing a finite collection of points, you're doing whatever. It's just the infinite frame bundle or something.
Exactly. Right? Okay, so again, this is the way to go from a VOA to this right D module, and we have this general framework which defines what a chiral algebra is, which is going to be a right D module with a certain morphism. I'm not going to get into the details here, but there's a way to phrase this in terms of morphisms of D modules, right? Push forwards and pullbacks of D modules. And in that world, you can define a chiral algebra as something very, very close to a Lie algebra, right? In fact, it's an algebra for the Lie operad, it's a Lie algebra for the chiral operad. Doesn't really matter. The thing is, we have a theorem that tells you that whenever you start from a VOA, you get this sort of thing. You get this chiral algebra, which now we have a product. Now we have some way of multiplying things over this sheaf. And we can do something very similar with the modules, right? So for the modules, we're going to define a chiral module very similarly, like with this abstract way, in the same way as chiral algebras. But then the really important thing is that when you fix the point, you can think of the modules for the original VOA as chiral modules for the chiral algebra, which are supported at the point, right? So we have two geometric constructions. For the algebra, we get a sheaf over the curve with some chiral product. And then for the modules, we have a way to insert them at the points, because when you think of a sheaf supported at a point, basically you only care about the fiber at that point. So that fiber is going to be the module itself, but now in this geometric setting, right? And the question is, okay, so for chiral algebras and chiral modules, you have a way to act with the chiral algebra on the chiral modules. How does this relate with the original actions of the VOA and the modules themselves, right? So this is very nice because we can see how the geometry comes into play with these actions. So now we're going to fix a certain amount of points and a certain amount of modules, and we're going to form these chiral modules inserted at the points. And now the question is, how do we translate the action of the chiral algebra itself on these chiral modules as something on the modules themselves, right? So we're going to look at global sections away from the points that we fixed of the chiral algebra, quotiented by something, it doesn't really matter. We can think of them as global sections of the chiral algebra with possible singularities, possible poles at these P's here. And we're going to view each one of these sections, how they act on each one of the modules, right? So we have global sections, but they're going to have different ways of acting for each one of the points. So say you fixed one of the points, you can look at the global section and write it locally with local coordinates around that point, and then you can write the action simply as a residue using those coordinates. And that's going to be really important because these are no longer formal variables. These are like the local coordinates around each point. But the expression is really similar to the ones that we were working with. Okay, so this is a way in which the chiral algebra will act on the modules themselves, and we can form the chiral complex now very similarly to the Lie algebra homology, to the Chevalier-Allenberg complex, if you will. Because now you can look, well, this was gamma 1. This was the first one that appeared in the complex, but then the other ones are going to be certain copies of those things. We're going to allow for singularities at the diagonals, not only at the points themselves, but also at the diagonals. But basically, the differentials in the complex are going to be constructed very similarly to the algebra homology, because whenever you have brackets between things in the algebra, you can now use the chiral product. And then when you have some element in the algebra acting in some module, you can use these actions here, depending on which point you inserted the module, right? So this is very nice because it relates both the algebraic and geometric parts of the theory. And you get this definition. Now this is a vector space. You can look at its homology, and you can see what happens and what information can you get from this complex. So the first thing we did was study this example. What happens at P1 when you insert some module C, whatever, at 0, and then the contragradient of some module at infinity. The contragradient is something defined in general by this formula here. You'll notice that it's like what one would define is that, but there's a weird thing here that we don't know why it appeared. Okay, so for now, believe me that that's a definition of the contragradient module. Now we're going to see how this naturally leads to a construction in the chiral complex. So as I said, the chiral complex has these gammas, and then tensoring by the fixed modules, and then you quotient by something, doesn't really matter. And now, for example, gamma 1 is going to be Laurent, well, one forms, but you can think of them as Laurent polynomials with coefficients on the vertex algebra, and gamma 2 will be the same in two variables, and so on and so forth. And now, for example, take something in gamma 1, right? Will be like a one form with z to the n at some integer, and something in the vertex algebra itself, some vector, right? Okay, but now this z is a local coordinate at 0. So written in this form, it's going to be very, very easy to make it act on the, now, how do we define D1 of this thing, right? We have to make the section act on each one of the modules, right? On the first one, on the one that we inserted at 0, no problem, because that is the local coordinate at 0, so we write it as always. But then at infinity, we need to change coordinates. We need to grab the section and write it in terms of c to the minus 1, which is the local coordinate at infinity. And then you get some weird thing that comes from that change of coordinates. But then the very definition that we have here will allow us to get rid of that. So basically, we have two weird things, which are the definition of the contragradient and then the changes of coordinate. And those two things will eventually kill each other, and we'll get a very nice thing at the end, which we can write in terms of the nth product of the vertex algebra themselves in this way, right? So we get a very nice formula for the differential in the chiral complex in this case. You can do something similar for the higher differentials, but it's not so small. Okay, so now what can we do with this chiral complex? It's been known for a very, very long time that the H0 of this complex is the dual of that, which is called the spaces of conformal blocks for this particular choice of thing. It's been known for a long time that this is just the space of V-module homomorphisms between the modules, right? So you grab some homomorphism of V-modules, and then you insert it in this formula, and it checks out. It gives you an isomorphism between these two spaces. You can read this, for example, in the Frankel and Ben-Swiss book. Then the first thing that we did this year was generalize this to H1, right? So now we got this result, which relates the chiral homology in the degree 1 of this very same thing with, now instead of homomorphisms, we need to look at extensions of V modules, right? So it's going to be an isomorphism to X1 of this thing. And it is very, very like concrete, and you can write it, like say you grab an extension here, and you write it like this, then you can choose splitting as vector space will give you a map going back here. And then you can use that to write sort of like a cocycle, and then you act outside of the section, and then you act inside of the section and see what the difference is. That will actually give you a map in the way that you want, so that now you can define something in the dual of the first chiral homology with this formula, which evaluates with this thing that you constructed here, right? So very, very concrete and very similar to the original one. See, here we grabbed an F and we put it inside this formula. So now we grab the section and we constructed something that we put inside this formula. So very, very natural, if you will. And this works, this checks out, and we don't need to impose any conditions on the VOA itself in order for this to work. So nice. And in particular, we can apply this to say, for example, there's a definition that we say that a VOA is rational whenever all of the admissible V modules are completely reducible, which is the same as saying that there are no non-trivial extensions between the admissible V modules. And so our theorem says, so being rational means that all of these are 0, right? So now we can say that if all of H1s are 0, then all of the extensions are going to be 0, and the vertex algebra is going to be rational. So we get this first corollary of our result. This result we got like in February, more or less, and then we took some months to write it down and publish it on the archive. But it's been done since the start of the year. And now what we're doing is trying to go to higher degrees, right? So now we have, for now, I don't know if we will be able to lift it later, but for now we will assume that V is C2 cofinite, which is a technical condition that will allow us to have finite dimensionality of all of the chiral homology groups, and also will give us enough projectives in the category of V modules, which is very, very important to have. Because then, for example, in the last part, I could only write extensions as Yoneda extensions, because we don't know if we have enough projectives in the category. But with enough projectives, you can do the usual extensions, right? So it's going to be much easier to work with them. And then we have a theorem. I don't know if I would call it theorem, because we went to write it down, and then we found some things. But will probably be a theorem by the end of the month, hopefully. And so if we assume C2 cofiniteness, we get this result, right? And there's a very, very nice way to write this in terms of grabbing an n-fold Yoneda extension, say, and then splitting it into n short exact sequences. And then each one of those exact sequences will give you a long exact sequence in chiral homology, which will come with certain connecting homomorphisms. And those connecting homomorphisms will allow us to lower the degree here. Say we started with some nth chiral homology, then we go to n-1, blah, 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 until the 0th chiral homology. And in the last step, we evaluate. So it's a generalization of the same construction that we gave before. And it should work without any extra assumptions. But with these extra assumptions, I think we were going to be able to write it down very, very clearly. Okay, so that's what we've been working with respect to the sphere, right? The sphere and extensions of V modules. There's another thing that we've been doing, which has to do with nodal curves that I said at the beginning. So now, let's go to another context. Let's fix a curve which is smooth everywhere except for a possible node. It has a node, and if we grab the normalization of that curve, we can think about it. There's a map from some x tilde, which is now smooth, which has 2 points, q plus and q minus. And those 2 points will be identified in X with a single point q, which is going to be the node, right? So that's the context now. And in this context, there's a phenomenon very well known, which is the factorization theorem. Now, for n equals 0 and V rational, it's been done by many different authors in different contexts For example, you can see here, I'm going to put the reference at the end. But say you assume that the VOA is rational, and you want to prove something for H0 chiral, right? So you have all of these things that I mentioned before, but now you have a queue, you have a node somewhere. So if you want to compute the chiral homology in this side of the thing, this theorem tells you, okay, you can go to the normalization, which gives you 2 points, and now you will introduce inside of each one of those points some irreducible module for the VOA at 0, and then its dual at infinity, or well, q plus and q minus. And you then grab the sum over all of the irreducibles of the VOA. So that gives you like a formula to compute the chiral homology in this nodal curve with respect to the chiral homology of a smooth curve, which is something that we've been working on very well. Okay, so this has been a theorem for a very long time for rational VOAs and for H0. Very recently, there's a generalization given in this paper, still for n equals 0, but for non-rational V's, which is going to be a little bit more abstract, because for non-rational VOAs, we can't actually talk about the reducibles, and this is not going to be a finite sum, and we have several problems. But there is a way to state this problem for non-rational VOAs. Okay, so what we've been working on in this time is, okay, let's try to abstract all of the things that we can in this situation. So the first thing we noticed is that this contragradient construction, in fact, we should actually look at it as a way to move from a V module to a right V module, okay? And the things that we've been working on that have been of the form C tensor A check, they should be thought of as V bimodules instead of just 2 left modules, right? And this solves quite a lot of problems, because thinking about V bimodules will give us a very nice generalization of this result. If you remember, I said that for any smooth point on a curve, you can identify V modules with chiral modules supported at the point. Okay, but that was for a smooth point. Now for a node in a nodal curve, we can do the same, but with V bimodules, right? So now we can insert at the node a bimodule, not a module. Okay, so the first thing what we do is let's try to take the nodal curve and insert the V itself, V as a V bimodule over itself. It's been known for a long time that in the smooth case, that doesn't change the chiral homology. That's known as propagation of vacua. And now we got that propagation of vacua also holds for nodal curves if we insert V as a V bimodule over itself, right? So that is the first very easy generalization. And then with some construction that relates to the Jou algebra, there's an algebra called the Jou algebra, which lets you transform V modules into Jou V modules, and Jou V is an associative algebra. It's a very, very classical object. And there's a way to induce, going back, right? So you take a module for this Jou algebra, and then you induce it to a module over the vertex, the VOA itself. And modulo some technicalities that we should check. There should be also an induction factor for B bimodules instead of modules. Bimodules instead of modules, which should be right exact. And then we have this. I think it is a theorem. It's just that I don't understand some parts of the proof. But I think we have this as proved. And it is basically a version of factorization which works for all n and for non-rational v's. It takes a lot of time to see why it is a generalization of what I just said. But it is basically here on the left side, we have a chiral homology on a nodal curve. And then on the other side, we have a chiral homology on the normalization. And we are introducing stuff at the 2 points. It's just that the stuff that we are introducing are now complexes of bimodules, complexes of modules, coming from a complex of factorizable bimodules, right? So it's a bit more technical, but in essence, it's the same thing. We're talking about having the chiral homology of the nodal curve and then computing it as something using some complexes of whatever in the normalization. Right? So in that sense, it is a factorization statement. And well, I put this a little bit of the proof, but I think we can skip that. It doesn't really matter. So yeah, I think that's what I wanted to talk about. Thank you.